One of the most important quantities you can ever study in mathematics or higher level technical mathematics is the notion of integral transforms. These are the generalization of the Fourier series to a continuous domain. In the Fourier series, the summation index, when you have to expand a function in terms of sine and cosine, is an integer. You can only have sine of nx or cosine of nx if you're looking at the interval negative pi to pi. So the integer n can only be discrete. It can take values from 1 to infinity. Or if you're using the complex variables, then the index goes from negative infinity to positive infinity, but again in integer steps. Integral transform is a generalization because the variable of integration is continuous. So alpha is a generalization of n. The integral transform of a function f of t by another function known as the kernel k of alpha semicolon t is called g of alpha. So you can think of the t variable as being integrated out, leaving us with just the alpha, and so the function is a function of alpha. There are several classes of integral transforms, in fact several dozens, and we'll only be looking at a few. The most important by far for us is going to be the Fourier transform and the Laplace transform, which we will study in great detail for the rest of the course. The Fourier transform definition, each case the kernel just changes and the range of integration also changes. So k alpha t is e to the minus I alpha t. This makes sense because when you look at the Fourier coefficients in the complex case, any function f of x can be written as the sum of cn e to the I nx from n equals minus infinity to plus infinity, where cn itself is the integral from whatever variables you have, like minus pi to pi with some normalization coefficient which is 1 over 2 pi, f of x e to the minus I nx dx. So that's the basis of this definition. You are trying to get cn's, which are now g alphas because the analog of alpha is n, through this procedure. So the kernel has to be similar to that. So that's why the kernel is e to the minus I alpha t. And the value for a and b are now going to be from minus infinity to plus infinity. So this is very general indeed. So the integral transform written as script ff or g alpha is going to be 1 over 2 pi. It's the same 1 over 2 pi that you get there. Integral from minus infinity to plus infinity of f of t instead of f of x e to the minus I alpha x, because remember the n has become alpha. So that is as simple as I forgot that x is now t, so dt. That's the definition of the Fourier transform. The next important transform we're going to have is Laplace transform, because the Fourier transform and the Laplace transform have huge amounts of application to both science and technology. The Laplace transform is especially useful in solving differential equations using the method of inverse Laplace transforms. So we'll be looking at that also in later weeks. The kernel now is e to the minus alpha t. So you can already see there's a very interesting relationship between the Fourier transform and the Laplace transform. Basically, if you rotate the Fourier transform from the imaginary axis to the real axis, you get the Laplace transform, and vice versa. So that's the connection between the Fourier and the Laplace transform. Also, the Laplace transform only goes from 0 to infinity instead of minus infinity to infinity for the Fourier transforms. So the Laplace transform, written script L of f, is another function g alpha, even though I'm calling them g, they're distinct g's of course, and that's going to be the integral from 0 to infinity f of t e to the minus alpha t dt. Now those who have studied anything like these things before may notice some interesting things about these integrals. They're first of all difficult to do integrals. If I have f of t to be something like sine, I'm already getting integrals that are not easy to do. And if it's more complicated than sine or cosine, you're going to get some very tough integrals. So this is another way to find tough integrals. If you can somehow find g of alpha by other methods, you can actually evaluate some very difficult integrals. Now there are other kinds of transforms, and I'll just mention two others. One is the Hankel transform, which has got a lot of applications in both chemistry and solid state physics. Here, the kernel happens to be t times the nth integral 0 Bessel function with a b from 0 to infinity. Now we will be studying Bessel functions in great detail, and for this reason Hankel transforms are sometimes called the Fourier Bessel transforms. So this video is more like a nomenclature zoology type video. So we'll try to study what they are later, but basically any function that satisfies the following second order linear differential equation with non-constant coefficients is called a Bessel equation of order nu. This is the order of the Bessel equation, and it's given with the Greek letter nu. The solution to this, if nu is a real number, is j nu x. Well, that is not what this is referring to. For the special case where nu is a natural number, that is 1, 2, 3, 4, etc., then you get jnx. Jnx turns out to be a nice basis, just like you have exponential functions. Jnx, the solutions to the Bessel equation, turn out to be a very nice basis to expand things in. So that's how you get the jn's into the picture. And you multiply it by t for reasons I can't tell you now. So the Hankel function, Hankel transform, is g alpha, which is integral 0 to infinity f of t times t jn alpha t. Or maybe I should tell you why you multiply by t. It turns out the asymptotic nature of the jn for integral values has got a t in the denominator. So you need to get rid of that t, and that's why you have multiplied by t. All right, I've gone and said it. Where jn is the nth order Bessel equation. And of course there's a dt here. And the last transform, although it's not the only transform left to discuss, is called the Mellin transform. The Mellin transform is especially interesting because it's closely related to what's called the beta and gamma functions, which we're also going to study in some detail in this course, because beta and gamma functions are extremely useful in engineering applications. So here the kernel k of alpha t is simply a polynomial t to the power alpha minus 1. Actually, I should be more accurately say it's a power function, because alpha is not required to be integer, from 0 to infinity again. So of all these transforms that we're going to study, only the Fourier transform extends to the entire range of minus infinity to plus infinity. So the Mellin transform, written as script m f, is another g alpha, which is the integral from 0 to infinity f of t to the power alpha minus 1 dt. Now if you have studied beta and gamma functions before, you probably see some things that you are going to see later. And one is the rational functional form of the beta functions. The beta functions and gamma functions have different definitions. So special cases of the Mellin transform end up giving us beta and gamma functions. So the Mellin transform of the function 1 over 1 plus t to the power p plus q is essentially beta function of P and Q. Again, I'll define beta later. And the Mellin transform of the function e to the minus t gives the famous gamma function as a function of alpha. Now, because both of them are Mellins of something, you can imagine that the beta function and gamma function themselves must be very closely related, and indeed they are. So this is one of your first clues that the beta function and the gamma function are secretly talking to each other. And later on we'll see the explicit nature of the conversation that these two functions end up having.